Hey Jesse, how you doing today? It is the start of office hours. What should we do? What should we do during this office hours? Let me know. I'll get my Pearson pulled up here. See what questions people have. It's the week before spring break, so I feel like everyone's taking the week off, but we can't. Tomorrow in class. I feel like attendance is going to be low, which it shouldn't be. It's a class day. Some people say, like, why do you hold class? And I say, well, we have class. We don't have spring break off. Data analytics in chapter 7, please. Yeah, Jamarcus, which part are you working on? Chapter 7 quiz. I tried looking at your other videos and got lost. Which part are you lost on? Canvas content 5. Chapter 7 quiz. Tell which of the residual plots indicate appropriateness of the linear model. Okay, let's look at that right there. So let's take a look. Assignment manager. There we go. Tell appropriateness of a linear model. So what does a residual plot show us? What does a residual plot show us? What does a residual plot show us? So let's go right here and put the timestamp. So Stat 201, Chapter 7. And quiz. And tell what each of the residual plots, where the points fall compared to, yeah. Well, so the residual plots show us, we'll go to it right here. When we get to the residual plot question, a residual plot shows us all the residuals at one time. So it shows us every single residual. And you can tell the difference with the residual plots that a regression plot is going to be the points with the line, but a residual plot is going to be, so we could take right here and go analyze, fit y by x. We'd predict the price by the capacity. And this is the regression plot, the scatter plot with the line fitted through it. So this is a regression plot. Now you see how this point is above, 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 below, 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 above. So what does this residual plot indicate to you right here? Now it's really easy to see it in the residual plot. Can you see, so Jesse, what does this residual plot indicate to you about the points? It's easier to see than up here. What do you notice about the residual plot here that's very clear? It's super clear in this residual plot. What do you notice about that right there? What do you notice about it? Very, very clear. It's a curved pattern. And it might be harder to see up here. You can kind of make it mimic that graphic. So I'm trying to make it so what you would need to do to make it exactly mimic it is you would need to take this graphic right here, and we do this quite often. We take this graphic right here, and we do the trick to turn it into a residual plot. You take it, and you make the line flat. So we go right here, and then we make the line flat, and you can see the curved pattern there. So your residual plot is basically the line flat, because anything on the line would have a residual of 0, and anything above the line would have a positive residual, and anything below the line would have a negative residual. So compare this right here, that graphic right there, to the plot you get down here, and you can see the similarities between it, that we can make a makeshift residual plot right here. There's the one above here, and it's just showing us a better distance of how far above and below they are. But look how above, above, below, 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 above, 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 there's the 3 points above to start, below, 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 and then got this large gap in the data. So the key is to see these things and understand that a residual plot, hey Nick, good to see you here, is just basically a flat line where the line has been set to 0, because we could just take this line right here and make it flat, and then anything on the line has a residual of 0, anything above the line has a positive, anything below the line has a negative. So those are the keys. So when you work on a question like this right here, you have to ask, well, what would these plots originally look like? So if you take this plot over here on the right, you could pretend for a moment that it came from something that looked like this right here. So now we're pretending there's a line going through it, and very clearly this one represents a what pattern. So now we're pretending that this is not the residual plot anymore. We're pretending it's the model, and we could turn it into a residual plot by taking it and making it flat. So if we were to take this and make it flat, we could see what the residual plot looks like. And we would just take this right here, make it flat. The line would need to be flat too now. But if we were to take this and make it flat, we'd get the residual plot. So what does this one here clearly indicate? Like there's the scatter plot, and then there's the associated residual plot. Once again, remember the residual plot is just taking the line, making it flat. And so you could do that right there, and the line would now go flat through it. It's a curved pattern also. So the other one right here, we've got another one. That's a curved pattern. And we're just pretending what this could have came from, because it could have came from many different plots. So this one right here, what pattern does it show? And remember, we're going to take it right here, pretend that we have a regression where the line is going up, regress through the model. So here's the model. And what do you see as a problem with this regression? The roller coaster, we'll do the roller coaster one next. It is thickening, so is it getting weaker or stronger? Is it getting weaker or stronger? So is that one getting weaker or stronger? So if it's getting thicker, it has more scatter, and the scatter is the strength. So if it's getting thicker, which is bad, we do not want it to get thicker or thinner in any spots. It's actually getting wetter as the model goes through. The model is it getting weaker or stronger? It's getting weaker. Weaker means more spread out, so it is getting weaker. The next one right here, that one a little bit, are they going to go for that? I think they are. So this one's a pretty good model, except for what? I think they're going for that. I think I see what they're going for. This one's a pretty good model, except for what? So here's the residual plot. Here's the associated scatter. It could have been up or down. We don't know which way it went. But the associated scatter plot could look something like this right here, and they're definitely going for that. That's an outlier right there. So they're just going for this right here, and you've got that one outlier right there. And once again, we can do these sorts of things, which is pretty neat. We can make examples like theoretical. And so we go right here, and we go to x is the vector 1 to 10. Let's go 1 to 5. Y is the vector 1 to 5. And then we're going to put a little of an outlier over here on this, and we'll show the same plot. But we'll put 8 over here, and we'll put 1 here. There we go. And m is given to lm, y tilde x, and then visualize model am. And we are making a linear regression of the variables. And you can see the 1 point down here below the line. So if I go to the residual plots of this, you can see right here, there's the original plot, below, below, above, 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 below. And then you go over here to the plots, and it's going to eventually show you the different residual plots. There's different residual plots we make, and I'm pretty sure the one we make in Jump is going to be one like this, the below, below, above, 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 below. And there's the residuals right there. So you can see the points that are pretty far away. And that's what we were looking at here. And we have this right here, below, below, above, 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 below. And there we go. So that's got it. Okay. And so, yeah, that identifies the problems. And we might have a good one. So it indicates with 1 point outlier, it's decreases, the model's predicted error decreases, and this one is a curved pattern. I think the one that usually gets people on this, the one people usually get wrong, is this one right here. This one shows a curved pattern right there, but this one's actually a good one. If the points are spread out and come together to be linear, is it increasing? If the points are getting closer together, it is increasing in power. This one is a pretty good random pattern right here. You want your residuals to look random, and so that's why this one is appropriate. A lot of people think this looks bad right here, but it's just looking pretty random. Remember, this is not the linear model. The linear model, if you were to graph it, would just have the points randomly scattered above and below it. So that's what we'd be getting at right there. And so we would have this. And now the points are kind of evenly scattered, and this would be a good model. So that's what we're looking for, is we're looking for a good scatter, and then that would turn into a good residual plot. So a lot of people don't realize, like, this is the ideal residual plot. It doesn't show any patterns, where this one has a pattern right here. It's weird because they have 2 outliers and a curved pattern. This one has a curved pattern, and basically you don't want to read their answers. You just want to be able to identify that one's getting stronger. That's curved pattern. That one's getting weaker. It's a curved pattern with outliers. getting weaker, getting stronger, outlier, and knowing what to look for in residual plots. Getting weaker, getting stronger, curve pattern. So when you get good at residual plots, you can kind of look at the plots themselves and say curve pattern, outlier, and getting stronger, excuse me, because it's getting tighter. So that's a really good question. I really like it. And understanding that a residual plot shows you all the residuals is kind of key to that one. A data frame of a data set of 91 roller coasters. Okay. A data set of 91 roller coasters. Here we are, data set 91 roller coasters. And this is at 12 Fall to 3, Stat 201, Chapter 7 quiz. Okay. So when we do this question right here, what are the variables in the units? Okay, so the predictor variable is, let's look at it. We got an R squared of 29.4%. Who can interpret the R squared right here? Now, this is very important. We are trying to figure out how long the ride lasts. So take a moment right here, see if you can do it. We're trying to figure out how long the ride lasts and using the drop to explain it in height. Chapter 7, student in stats. Yeah. So the reason I do this right here is because if you can interpret the R squared for these problems without any prompt, you're good for the test. I think a lot of times people are like, I don't need to practice interpreting the R squared. But that's one of the hardest things for people to do is to interpret the R squared on the test. But what would be the interpretation of R squared right here when we're trying to figure out how long the ride lasts in terms of seconds based on the drop? So the drop is the X variable, and then how long the ride lasts is the Y variable. So what's the interpretation of the R squared right there, which is 0.294 as a decimal, 29.4% as a percentage. And then a lot of people say, well, that's the correlation. No. R squared is not correlation. And the reason I bring questions like this to light is because I'm trying to teach to the test, so to say. On the test, we have you write written interpretations, so glossing over the R squared right there and not thinking about what it means is going to be a bit of a problem. So what does that R squared mean? So remember, the Y variable is how long the ride lasts, and the X variable is the drop in feet. So what would be the R squared right here, like interpretation? So how do we interpret that R squared? How would we interpret it? Very, very important. So if you're here watching right now, see if you can do it. It's blank percent of the variation in Y is explained by the variation in X. So you have to plug in the R squared, and you have to plug in the Y, you have to plug in the X. So blank percent of the variation in Y is explained by the variation in X. Blank percent of the variation in Y is explained by the variation in X. And if you only practice writing it out right before the test, but if you practice writing out now, then you get to the test, you're like, oh, I remember how to do that. And you practice writing it before the test. So the more practice you have, the key. If you're watching this right now, try to fill in 29% of the length of the ride of the variation. Oh, good job, Jesse, right there. But remember, 29.4% of the variation in length of the ride can be explained by the variation in the drop of the ride, the drop in feet of the ride. Does that make sense? 29.4% of the variation in length of a ride in seconds can be explained by the variation in the drop of a ride in feet. So blank percent of the variation in Y can be explained by the variation in X. Kind of key right there. Variation is a key part of it because we're trying to understand the variation in the Y variable, and we're using the variation in the X variable. X is along the X axis right there to explain it. So how much of the variation, if you look over here at the model I made previously, this model explains a lot of the variation, maybe a good bit. The R squared of this model is, it's only 0.6. That's nothing. But watch this. Jesse, can you tell me right now, what is the R squared of this model? And then think about what that means. Like, look at it visually. Visually over here, that line explains how much of the variation in the Y values. So Y varies from 1 to 5, and this line explains what? So you can, like, understand the R squared. It's also correlation squared. So you can tell the correlation here probably, because all the points are directly on the line. Great job, Jesse, right there. So this one has an R squared of 100% of 1. And that means 100%, because 100% of the variation in the y variable is explained by the variation in the x, and it makes the linear model. You could also have, if we went right here, let's times these by -1. Here, we'll do it on the y. So now the line goes downward, but still 100% of the variation in y is explained by the variation in x. So that's kind of key right there when we think about it, that the variation in y explained by the variation in x, not 1% though, this is 100%. So r squared is often reported as a decimal, but when interpreted, it's interpreted as a percent. Those are key things to see, hence why I go over it, because r squared is going to be correlation squared, but when you interpret it, we interpret it as a percent. So it's going to be from 0 to 1. And then when you interpret it, you multiply it by 100. So key things to notice. What are the variables right here? The predictor variable is, so we're trying to, the predictor, oh gosh, I hate these words. The response variable. Yeah, I love response. Response variable is we're trying to figure out how long the ride lasts, and that's going to be in seconds. And then the predictor variable that's going to predict the duration is going to be the drop. And the units of the drop height in feet. So it is in feet. There we go. The slope would be, I think so. What units does the slope have? And this is where it gets all tricky. Okay. That's going to be how many feet it drops per second. Yes. Or wait a minute. Let's make sure we didn't reverse things, because that's where it gets tricky. A data set of the roller coasters in addition on one tower is usually having a large drop but a short ride. After setting aside a regression model to predict duration from the drop. Okay, so we're trying to predict the duration. So it's going to be how many seconds it lasts per foot. So, wait a minute. How many, okay, for each additional foot. Oy, the X and the Y always get me a little mixed up right here. We don't ask questions like this on the test because it's for each additional foot, we expect the ride to have this difference in how long it lasts. So for each additional foot, yeah, it's seconds per foot. I think so. That sounds right. Is the slope probably positive or negative? So it's weird because if a ride were to drop from like 1,000,000 miles higher, it would probably have a longer, but let's see here. It's not the R squared. Coasters with bigger drops, here it is, probably provide shorter. Okay, so it's a roller coaster. Yeah, so a roller coaster with a low drop is not going to. So a roller coaster with bigger drops probably provides shorter rides. The slope is probably negative. Hopefully got everything right. Oh my gosh, with the, no way. There, really? That one I'm a little bit iffy on because when you think about it, it really, there's other things that come into play too. So I'm glad we do these sorts of questions because the last one right there, it's saying roller coasters with bigger drops probably provide, it kind of makes sense. They have to build up the speed, right? The slope is probably positive because roller coasters with bigger drops probably provide longer rides, which is a positive relationship. So it's saying if you were to ride this roller coaster here versus this roller coaster here, then this one would be longer, I guess because you build up more speed, right? And this one would be shorter. This one has a lower drop. Does that make sense, Jesse, right there? That last one's a little tricky, and I'm glad we do some of these because it's like, okay, wait a minute. To me, I was thinking if you have a small drop, then the roller coaster is probably going really slow. And a slow ride's probably going to be a while, like, you know, the roller coasters you ride when you don't really ride roller coasters. But some of those big roller coasters get you going and you go super fast and then the ride ends. I am not a roller coaster enthusiast, so that was not my expertise. Once again, glad why we do these. The key thing right here, if the slope is positive, then the relationship would be coasters with bigger drops provide longer rides. If the slope is negative, then coasters with bigger drops would supply shorter rides, and that's because it is a negative or inverse relationship. More important to know that than to know the theory behind roller coasters, because we're not testing you on your roller coaster knowledge. We're testing you on positive slopes indicate a positive relationship, where negative slopes would indicate a negative relationship. So that's more important right here, that these two would go together. So if you were to get it wrong, you'd want to get it wrong like this. But you want to get it right, though, that coasters with bigger drops provide longer rides, bigger drop, longer, positive relationship. And once again, the other one would be bigger drops, shorter rides, negative relationship. So those are the key learning objectives, which we always try to go for right there. And why we sometimes do a problem because, yeah, a little tricky right there. A little tricky. I like to call the X the explanatory variable. The table shows the number of live births. There we go. I think we've done this one. We can do it again, though. Table shows live births. Oh, and we got intro stats class. Here we'll do the table shows, or we got a student in an intro stats class. A student in an intro stat class. Oh, there's that one. A student in the intro stats class. We go. Is it this one right here? Student in intro stats class. One question wrong. We can't get any more wrong today. That's our one we get wrong. Only one wrong. Stat 201, chapter 7 quiz. A student in an intro stat class. She wants to model the relationship between student jobs and GPA. She collects a random sample of students and asks each student their GPA and numbers of hours worked. She checks the conditions, makes a linear model. With the GPA as the response variable, that means it's the Y variable of interest. She finds the R squared to be 12.7%. What is the correct interpretation? Do not look at their interpretations, write your own. So we have here R squared is equal to, So go ahead and interpret it. You got it, Jesse. So don't read their responses. Y is GPA, like you said. X is hours worked. And we do blank percent of the variation in Y is explained. And we have a little X explained by the variation in X. So blank percent of the variation in Y is explained by the variation in X. So how would we interpret this? Don't even read their responses because they're gonna do it a little bit differently. But you see, it all starts out with basically what we have to start. There are other ways to explain R squared, like Dr. Putri likes to say, knowing someone's hours worked would get you 12.7% of the way to understanding the variation in their GPAs. 12.7% of the variation in GPAs is explained by the variation in hours studied. Boom. Or it's hours studied, is it? Yeah, I guess hours studied makes more sense. 12.7% of the differences in hours worked can be accounted by a linear model on GPA. 12% of the changes in GPA can be accounted for by oh, but they reversed this. No, this is reversing the X and the Y. 12.7% of students' hours work can be accounted for by, oh man, they really do some weird explanations right here. 12.7% of a student's GPA is accounted for by whether or not, no, this doesn't even mention the linear model. Whether or not they work is categorical, so that's totally changing the name of the variable. So that one's wrong because it's not work, yes, no. It's the linear model created from another quantitative variable. It's not a categorical question, so that's just theoretically wrong. This one's close-ish. That's decent. 12.7% of the changes. We don't really talk about changes. This one right here, let me look at it again. 12.7% of the differences in hours worked can be accounted for. No, this one's switching the X and the Y. So changes is not what we care about. So I'm a little worried. Let me look at this one again. 12.7% of the changes in GPA can be accounted for. I don't like that they're calling it changes. Because if they said 12.7% of the variation in GPA can be accounted for, I think that's the one they want you to do because they are talking about a linear model. 12.7% of students' hours work. I'm pretty sure it's this one. Yeah. Yeah, I don't love what they're doing, but there's some inherent problems with at least two of them that I see like can't be the answers. This one right here turns it to a categorical variable. That's just flat out wrong. Like that, no, that's categorical variable. This one right here switches the Y variable, talking about the differences in hours worked is what we're trying to understand with a linear model on GPA. So that switches the XY relationship. So that one has to be wrong. So we've already eliminated this is wrong because it switches the XY relationship. And this is wrong because it treats the categorical variable like an X variable like a categorical. Then this one right here, 12.7% of students' hours worked. It doesn't talk about variation or differences or changes. And so that's why I was like, I talk about the variation explained in the y variable. They also mentioned linear model right here, which is a decent idea. You could say that, like we could add that onto ours just to be more thorough, to say 12.7% of the variation in students' GPAs is explained by the variation in their hours studied created by a linear model. Like it's a little extra, which is good. There was nothing wrong, and this says accounted for, which is like explained. That one does too. But I think the changes right here and the linear model is what pushed me over. This is not a horrible explanation. That's my only problem, is like, that's not horrible. You'd probably get some points on the test for that one. I'd hope the graders would, like, this is like, these would be like 1 point out of 4. That's like 2.5. Probably have to count that right there. It's a little bit weird. Got another one, and then I think, yep. So that was a little tricky. I like tricky questions, but that's once again why we write out our answer and we can see some differences. We were able to eliminate 2 of them. We got Jamarcus had a question. Here we go. What's this one over here, right? Okay, this one is a bit of a longer problem. It's got a lot of steps to it. So with this problem right here, we got to do quite a few steps. Okay, let's do steps for this problem right here. With this one, I think we pretty much have to make the model. So, no, I think you gotta use jump, basically. I would use jump, because using jump is going to make it a lot easier, and it's going to give you practice for the data analytics 5. So if you do the steps right here that I'm about to do, you'll also be doing data analytics 5. So this is how we do it right here. Now, there's a problem, and they do mention it right here, that the years listed are listed like 60, 65, 70, 75. It's years since 1960. So 1960 is 60. And so when you look at this right here, what kind of relationship do you see with the birth rate? The birth rate is doing what? Which we can answer the first one pretty clearly by looking at that. Going forward in years, the birth rate is what? And then that means the answer is what? So we don't really need to make it in jump yet. It would help, but we should be able to see the pattern in the data. It's declining. Boom. Answer right there. You see it's going down right there as years go up. So that's going to be the first one. Now to do it in jump, we're going to go here to copy to clipboard, and we're going to copy like this. Control C. Go over to jump, and inside of jump right here, we want to go to File, New Data Table. File, New Data Table. Negative relationship. Great job, Jesse, right there. That's the direction. Once we go into the new data table, we're going to go to Edit and Paste with column names. Edit, paste with column names. And if you don't do that, it will look like this, and that is not correct because it's categorical. Make sure to restart and paste with column names, and they'll be blue. Now, what you can do, that's the easiest thing for most people, is just to rewrite the year. So if you rewrite the year right here, you can make it so it's years since years since 1900, excuse me. There's also another way, and we'll just call this year 2. There's another way, which if you know some tricks you can do, if you right click, and you don't have to do both these, go to Formula, take the year and subtract off 1900, then apply that, you get the column right there. So there's just a few ways, but you have to make this column right here to get the proper analysis. Don't use this column right here. You could rewrite it, or you could formula it. Just writing it, make sure they're blue. If they're not blue, they're categorical. Just to show you, we'll go here and type hello, and it'll turn it to red, which is categorical. So don't do that. That's just kind of showing how jump works, and they have to be blue to do quantitative scatter plots. So we're going to go to Analyze Fit Y by X now. Analyze Fit Y by X. We're going to use the year variable we created right here because it's years since 1960. Put that as the X variable, which was on the X axis in our original graphic, and look at the rate as the Y variable. Now, as we saw in the original graphic, once we click OK, we're going to see the downward relationship with the 2 kind of points that are further off. We're going to fit the linear model by clicking the red arrow and going to Fit Line. This will fit the linear model to the data right here, and you can see it's a pretty good fit. 80% of the variation in the birth rate is explained by the variation in years. 80.1 if you want to be exact. 80.1% of the variation in birth rate is explained by the variation in years. Now, we're going to go ahead and round these right here because I think it says round to 3 decimals on these. And then let's interpret these coefficients. So we'll put that to year, and there's the coefficients. And you should also know that the coefficients are down here. The estimate of the intercept, which is B0, is 25.651. That is the predicted birth rate for 1900, because it'd be 0 years since 1900. So the predicted birth rate for 1900 is 25.65 in birth rate units, whatever it is, births per thousand or so. We do some canvas condom. The slope right here is negative, and there's the slope down there. Know that this is B1, which is the estimate of the slope, and also the model is statistically significant due to the p-value of the slope. So we would say that for each additional year since 1900, we expect the birth rate to decline by 0.114 births per thousand. I think that's the units right there. So for each additional X, we expect Y to decrease or increase by B1 on average. Throw a little on average there. So interpreting both the intercept, the slope, and the R squared is very important, and knowing your output. So try to pause on this screen right here. Pretty much everything on this screen, well, not everything, but the R squared, the intercept, the slope, and the p-value are the things to know. R squared adjusted, which you don't need to know. I'm going to mention a few things you don't need to know, but in case anyone wants to know the rest of the output, R squared adjusted is the R squared after accounting for the multiple model. So it's a R squared that's penalized. Root mean square is the typical miss the model makes. Mean of the response is the mean birth rate. Number of observations is how many dots there are. Estimate is B0, B1, the intercept and the slope estimate. Standard error is the uncertainty. T ratio is the ratio of your estimate to your uncertainty. And the p-values are the statistical significance for both of those coefficients. And the only statistical significance we care about is the significance of the X variable, which is the significance right there. And that's just kind of a quick overview of what we have for the output. Know your output. Know the things we should know, which I went over first. Hey, Kat, good to see you here. Describe the trend. It's decreasing over time. And what's really great is we can take our output over here and just drag and drop a lot of these answers in. So we're going to go right here, put this over here, and we need to 2 decimals. So let's just take this answer right here to 2 decimals, and this one to 2 decimals. There we go. Check the assumptions. Now, this is where it looks mostly linear and a little bit of outliers. Let's see. Yes, because the scatter plot is really strained, there's no outliers. I'm trying to remember if they call those outliers. They're a little bit away. We'll find out. It's always, I would mention this. I'd say we can't tell for lurking variables. Lurking variables, you'd have to test them in the model. I can't think of a good lurking variable to say lurking variables are variables outside of the year and the rate. That's a wrong answer right there. It's either going to be yes, because it's reasonably strained, there are no outliers. Also plot not thickening. And then we might have no, it shows evidence of light outliers. Yeah, definitely. On the test, we always make it clear if there's outliers. Like here is clear outliers right there, and here's clearly plot getting thicker down here. Remember, if it gets thicker in any direction. So this is how we like to make stuff look on the test, where there's clearly an outlier down here, and it's clearly not plot thickening, where over here there are no outliers, and it's just plot thickening. So we prefer that on the test then. Is that an outlier? Is that an outlier? There are ways to look at this and to save certain things for the model. Like we could go here and look at, where is it? We could save the residuals and all that good stuff. There's ways to look at this with advanced regression to know how big of outliers there are. Interpret the slope. It's for each additional year. Nope. The number of bursts per 100 is changed by an amount equal to the slope per year on average. The slope is the number of bursts per 1,000. No. That's the intercept right there. The table gives rates as intervals. Estimate what the rate was in 1978. So to solve for this, we have to plug in 78 right here. So we go right here, and we're plugging in 78 because it's years since 1900. 78 times this plus 2565. There we go. And there we go. That can't be right. Oh, no. Because I'm looking at this. What I did was, if you notice, is I didn't subtract. So because I didn't subtract, I got a very wrong answer. And we're doing 78, right? Be careful. If you don't subtract, and you can look at the model over here, we should be getting 78 somewhere in here-ish, and that looks more accurate to where 1978 would be. So look at your model while doing this, and we would say right here, the model predicts that for the 1978 round to 1 decimal. Here we go. Now, if this is the prediction, what is that value, Jesse, in notation? And this is an important notation thing to cover. that we talked about yesterday, if that is the prediction in notation, that would be known as the what. And make sure to know all the notation on the screen here. Mean of x, mean of y, actual, predicted, x value, the r squared, the slope estimate, the intercept estimate, correlation, and residual. So it would be y hat because that is the predicted value of y right there, y hat. So then they're saying the actual is this. So when we know the residual formula, actual minus predicted, 15 minus 17.1, then we get the residual. And that means it's under the model. Now, that's not exactly the point, or is it? No, it's not. But it's kind of close-ish to it. So the model predicted this many more bursts because the model is above it, and the residual is thus negative. The residual is this difference between the actual and the predicted, and negative residuals are below the model. So it predicted this many more bursts right here. Okay. The birth rate in 2020, so we've got the birth rate in 2020, was not yet available when the data was collected. Make a prediction. So that's going to be 120 years past. So we're just going to plug 120 in right here times this. And we're going to subtract 2565 minus this. There you go, 1245. And so there's some faith in this. This is not too big of an extrapolation. It's over here on the edge, but it is an extrapolation because it's going beyond the model. And you can see that right here. There's no data. Extrapolation is when we leave the model. You could also extrapolate on the low end, which the intercept is an extrapolation too. But anything outside of this data range right here is an extrapolation. Oh my gosh, Jesse, 100 points. Whoa, it's probably why I was making some errors over there. Wow, you saved me messing up a question right there. That is a negative. I remembered that while I was doing it, but I didn't include it in there. And that is right there negative. So if you don't include that, you do lose points. I was solving it through that way when I was solving all the questions. Don't make that error, though. Jesse, great catch. Another 100 points. I would say there is some faith in this prediction right here because it's not that large of an extrapolation. So we're not going that far outside the model. But this one over here at 250 is a very large extrapolation. You're well outside the model at this point, but we can just plug in the values and the equation makes predictions. So we go right here, 150 times 1, 25.65 minus that value, 19. And we got to make sure we're rounding 1 decimal. There we go. I wish they just counted it if you added extra decimals. That's one of my small complaints. But if you ever get something wrong like that, let me know or your teacher. I do correct those things. Can be a lot, though. I get a lot of emails, but I do like them. I want to make sure you get your points. If you typed in extra decimal, you should get the point, I believe. Come on your faith. I would say there is no faith because it's a big extrapolation. Because expected birth rate is, it's not negative. So, but it is going to be, there's no faith in the predicted value because extrapolation is far beyond the data. Now, the only one I'm concerned about here, those aren't that big of outliers right there. So I think we got everything. Yep, we did. These weren't really that big of outliers. I've seen way worse, and we do try to make it more obvious. So I was a little bit concerned about the question back here. Are they outliers? And it was hard to say for certain. Checking with one of the advanced ways right here using the fit model, and this is just advanced stuff, we can go right here and add in the variables, and we can see a more advanced regression right here. And let's look at the points with an influence. Where's Cook's influence? Okay, so now we're looking at the influence of those points. And the most influential points are these points over here. So those points, let me highlight them in the plot, look to not have undue influence. And this is how we would do the analysis. We'd look at the amount of influence they have. The most influential points are these points back here, probably due to their leverage, which is their distance on the x. And this point right here and this point right here. No, that is the most influential point over here, I think. Yeah, okay, that's the most influential point. It dictates them all the most out of all the points. So a little concerning. The other one's very close to the mean of the x's, not giving it high influence. Cook's D is a measure of influence to tell how much a point is influencing the model. Points with little to no influence, like these points over here, if the point was removed from the model, then the model would not change much. So to show you right here, auto recalc influence, if I remove this point right here, which has no influence, the model doesn't really change. You saw a tiny bit of a change right there. So if I go to clear row states, you're going to see the model really not move it much. But this point right here, which has high influence, which that's a little concerning. When I remove it, the model changes a lot. Notice how the bands and the confidence changed a lot. So the model really drastically changed right there with that point removed, because that point has a lot of influence on the model. So clearing the row states again will bring it back, and you'll see a change to the model. More drastic because it has higher influence. But that's how we can analyze stuff with more upper level statistics to find the most influential points in the model. And no points should have a large amount of influence. Like, look at this right here. This point right here has basically no influence, where this point, a ratio, has like hundreds of times more influence on the model. So why would you want one point having 100 times more influence on the model than another point? Like, that point, if you remove it, model really doesn't change. But this point has the majority of the influence in the model. These other 2 points have a lot. So the model is really being dictated by 3 points. 3 points play the majority of the role of creating that model. And then, so you'd say, got a model highly influenced by just a few points. Do we really want this relationship to be created from just this data? And that's how we do a little upper level statistics. So those are the concerns, but overall a good model, because no model's perfect. All models are wrong, some are useful. Next question. I like to mention a little bit of that stuff because sometimes people wonder, like, well, how would we know this? How could we possibly, like in statistics, give a thorough answer? Like, because sometimes we say, look at the plot. And you're like, wait, what would we do if we look at the plot? We can look at more, though. We can get a lot of analysis. We'll do the Canvas content here coming up soon. Got a random sample of records. Here we go right here. A random sample. Yeah, Jesse, awesome. Let's do this one right here. And this is... Okay, a random sample of records. Sales of homes in a city gives the price and size in square feet of 117 homes. A regression to predict the price, Y variable of interest, in thousands of dollars, and size has an R squared of this. Write a sentence interpreting the R squared. Write your own sentence in the chat. Give it a go right now. Write your own sentence interpreting R squared in the chat. Don't look at theirs. Don't look at their answers. It's going to be blank percent of the variation Y is explained by the variation X. Oh, I think Jesse's done it. 72.5% of the variation in price is explained by the variation in size. So a linear model on size. So we're trying to figure out the price. Oh, I think this is it. Really? First one. A linear model on size accounts for... No, but it's the wrong number. So look, we can narrow it down to 2 answers right here by looking for the right percentage. A linear model on size accounts for 72.5% of the variation in home price. We're trying to understand the variation of home price. So that's the Y variable of interest. So a linear model on size, which is the X variable, explains or accounts for. So that's where they're using the explain, like blank percent of the variation in Y is explained by the variation in X. They're just reversing it to say 72.5% of the variation in home price is explained by the, or accounted for by the variation in size, or price right there. So little change up of how it's done, but once again, we should understand the small differences right here and see that the Y variable of interest is home price. So we're trying to understand or account for the variation in home price. Does that make sense, Jesse? Kind of the key right there, the variation in home price is what we're trying to understand. Good stuff. Yep. It's they really try to hit you with different ways of reading and understanding it. So the more you take a look at it and understand the small differences, the better you can do. And so it's pretty good because, even though... So what I used to do is I used to say there's many ways to interpret R squared. And when I got to the test, people would just combine different ways into some sort of crazy way of doing it. And then it wouldn't make sense. So nowadays, and one student said, why do we have to learn this one particular way of interpreting it? And I'm like, because grades are better. Because students do better when I say blank percent of the variation in Y is explained by the variation in X. Blank percent of the variation in Y is explained by the variation in X. Because you could say knowing X gets you blank percent of understanding the variation in Y. That's another way of doing it. You could say when we try to understand the variation in Y, we get this far by knowing the variation in X. There's so many ways to do it that are kind of synonymous. But the more ways I offer you, when you get to the test, if you have to write it out, then you're like, wait a minute, how do I do it again? So I go memorization. There's very few things I go with very rote memorization on, but this is one of them. Awesome. Let's do some Canvas content. It's time for some Canvas content. Canvas content number 5. Canvas content. Okay. A little canvas content here. Stat tool 1. So a really big thing, we do a few versions of this. So write these down, put them on note cards, put them on flashcards. Remember, we're going for knowledge right here. This is data analytics number 5. Whoops. Or go, whoops, one button. Flip around right there. We're going for canvas content number 5. Canvas content number 5. Here we go. So remember, we're going for knowledge right here, which is the key. We're trying to understand this. Adding together all the residuals will always sum to 0 on average. We don't even need on average. Well, take a look at the residuals right here. We made a model earlier. We'll make the one where I didn't have it as a perfect model, and we can get the residuals right here. So here are the residuals. Oh, they're so small. Let's go right here and do this. Let's go to empty cars and go to rows 1 through 5. So let's go here, make a model predicting horsepower based on weight of data, and here's the model. Okay. This has a positive residual. Positive, negative, negative, positive. The way the line works is the line goes through the center of the data, reducing the sums of squared errors. And you could literally take all these residuals right here and add them up. It's going to be just a little more here. And since the line goes through the center of the data, R is going to not carry every decimal, but it's going to be close. You basically get, and you do theoretically get, 0. Because, and there, oh, it did it. I love it. I love it. So when you add up all the residuals, some are above and some are below because the line's cutting through the middle. So everything would average out to the line. Just think of these points like squishing in around a line. The line is going through the center of them. The line is kind of the average of the points. And that's why you want the line to go through the middle. So it should be kind of the average of the points at all points. And the linear model does that. So when you add up all the residuals, you get 0. That's why adding them up is not interesting. What is interesting is taking the residuals and squaring them and finding the sum of the squared residuals, which is the sum of the squared error right there. And that's the remaining error that we have not accounted for. So that is what's interesting, is finding the sum of the squared error, because the residuals, when you sum them up, get you 0, and that's always the case. So adding up all the residuals will always get you 0. That is very true right there at all times. Consider the jump output. So once again, you should know the following in the jump output. You should know here the intercept, you should know here the slope, and you should know the R squared. So the intercept, the slope, and the R squared are what we should know. So with this in mind right here, we have the intercept is going to be when age is equal to 0, we expect finish time to be 156.5 seconds. Now that is illogical because you can't have an age equal to 0. The slope would be for each additional year someone is older, we expect their finish time to be 2.4 seconds longer, because I think this is in seconds. Oh, in minutes, 2.4 minutes longer. And the age is 0, we'd expect 156 minutes. They're super fast as babies. 34.4% of the variation in finish time is explained by the variation in age. So try that right now. Try interpreting all 3 of those things. Interpret the intercept, interpret the slope, interpret the R squared, and know that the p-value of the slope is the statistical significance of the model, i.e. this model is statistically significant because the slope coefficient, the one associated with age, has a p-value that is below 0.05. These are the things to know from this output. Interpret the intercept in context of the problem. When someone's age is equal to 0, we expect their finish time to be equal to 156.52 minutes. When x is equal to 0, we expect y to equal b0 on average. Sprinkle a little on average on there. Next, interpret the slope. For each additional x, we expect y to increase or decrease by b1 on average. So for each additional year, we expect someone's finish time to increase by 2.44 minutes on average. And then next, interpret the R squared. For blank percent of the variation Y is explained by the variation X. So 34.4% of the variation in finish time is explained by the variation in age. What does it want us to do? It wants the R squared. 34. Look at that. We even get an interpretation. Nice job right there. The slope. So slope is going to be the 2.4 right there. And then the intercept was 156, right? Double check your values. Make sure you got the right ones. And you're good to go. Find the predicted value. So what we would do right here is we're going to write the regression equation. So write the regression equation. The regression equation is y hat equals b0 plus b1x. So when we make a prediction for y right here, we have b0, which is the intercept. Good to see you, Jesse. And then b1 is equal to 4. And then the value of x is going to get plugged in to predict y. So all we're doing is plugging in x right here. 6 times 4 plus 11, and the predicted value is 35. So that's all we're doing, just knowing your notation. If the residual is 1.2 and the observed is 24.6, what was the predicted value? So this one is really great because you can solve it theoretically very quickly. And I'll show you the notation on it. But a positive residual means the point is where? It means it is above the line. So if you know this right here, you would know this is equal to 1.2. That's E, and that's the residual right here is E. And the observed is going to be the upper value we're looking for, the Y, and we'll figure out what that is. And then the Y hat, oh, the observed is, and the observed is that. The observed is this, 24.6. And it wants the predicted, the Y hat, which comes from the line. So you know the distance that the value is 1.2 above the line. So you could just subtract that and get 23.4. So you can plug this back into the formula that the residual is equal to the actual minus the predicted. So that was the observed, and we're solving for the predicted. And so we would get here that 1.2 is equal to 24.6 minus y hat. And simply algebraing this out will find you the value right here because you can subtract from both sides. You can take 1.2 and minus 24.6, and that is what minus y is equal to. So minus 23.4 is equal to minus y hat, meaning that 23.4 is equal to y hat. But preferably, I like to do the way over here on this side, because if you know that the residual is 1.2, you know the point is above the line. Remember, positive residuals denote something is above the line, and thus the point would be above the line by 1.2. So the predicted was 23.4, and it's a lot quicker of a solve to do that. So you can check it both ways, which is good. For each 1 unit increase in X, we expect Y to increase or decrease by B1 units. Technically, it could be decrease here, but you could also say increase by negative, so that would be accounting for that, and that is the interpretation of the slope. So really good stuff right there. We should get that 100. We did. We'll do another preview of it. Knowing it is very important. If the residual is this, then what was the predicted value? We just did one of those. Since the residual is positive, we know it's that far above the line. So once again, the better you get at this, I would still solve this out. The quick solve on this is going to be the following. We're doing a quick solve on this one only because we have here a line and we have here the observed, which is y, and the residual, which is e, and we want the predicted, which is y hat. So the y hat is what we're solving for. The e right here is equal to 0.6, and the observed is 29.9, and that makes this 29.3. Okay. If the residual is positive, which one is larger? Well, we just saw that right here. This one gives it away. The observed is, which is the actual. The observed is the actual. The predicted comes from the line, and we already solved this, and we had a positive residual. So these are a perfect combo of questions where we can see that the observed dot up here, which is the value of y, is higher than the predicted value. So very, very good right there. Adding together all the residuals will sum to 0. True. Make a prediction. Well, this one we did earlier. We're going to just take right there and plug 6 times 3 plus 11, and we get 29. Double check your work. Be very careful. If the correlation is equal to 0.5, what is R squared? So R squared, if we know our notation, can be found by doing R squared. And correlation is R, so it's saying R is equal to 0.50. So what is R squared? Now, R squared is reported as a decimal, interpreted as a percent, but it's reported as a decimal. So R squared is equal to 0.5 squared, which is 0.25. There we go. Yay, 10. I thought it said I got a 7 there. I was like, what? We'll do one more attempt at this right here. Let's take a look. And we did this one earlier. Make sure to interpret all your output. Make sure to interpret all the output right here. The slope was... There's the slope coefficient right there and right there. And the intercept is that right there. Find the predicted value, just plugging in 8 times x plus 8 times b1. There it is right there. What was the predicted value? Well, it's positive. That's very similar to the one we got earlier, 23.4. That's the interpretation of the slope right there. And if the residual is positive, then the actual was higher. So the more you practice these, the better you get. And yeah, it's just getting it down, understanding what to interpret, what it means, knowing the output from R, or not from R, from jump. That's the advanced output right there. But know your output. We went over this a lot. Knowing what the intercept is, the slope is, and they're also found down here, the statistical significance of the model, knowing also the R squared, knowing that we can get a residual plot right here, which shows us the plot of all the residuals. Very important. And there's the residual plot with the 2 points above the line at the end, and you can see them. Oh, that's at the back. Darn you, jump, flip in the plot. There's another one right there. So there's the 2 points above the line right there. Why is that reversed? Did it close down one of my residual plots? Hate it when it does it. There we go. Residual plot by X right here. So there's the points right there. And there's the points at the back. Yeah, so there's the 2 points above the line. And so there's many, many ways to do this. I do like that one right there. Normality of residuals. We just asked you, I think, to get the first plot right there by the predicted values. So make sure to follow the instructions on the data analytics. Any other questions right now? What other questions are there? Let me know what you're thinking. So if you have a question, feel free to share it over the main screen. We've done a lot today so far. Might take a little break here. Got a big event coming up later. So no, we don't have anyone here. I think spring break is limiting the amount of people here. We might end early because I'm going to go help some people on Discord. But we got a lot done today already. Got a lot of questions done. In chapter 7, we got a lot of time. So we'll be back here next time. Thank you, Jesse. Thank you, everybody. Until then, bye for now. We'll see you later. Bye.